to some extent before. We are looking at building regression models with functions. So you do this as early as Math 1 because you do linear regressions in Math 1, which is where you just basically like make a line, right, to fit your data points. And then we can also do that with quadratics. You probably have not done these with like a cubic or a quartic, but the steps are really pretty much the same. This stuff is where I think is some of the coolest stuff that we do in math. In fact, in a couple years, they are going to like revamp our math courses again. And currently, the plan is for you to do Math 1 and Math 2, and then there will be no Math 3 or 4. There will be a class that's basically a modeling class where you like spend a whole class doing a lot of this stuff right here. Although there'll be, I think, some other stuff in there, and then the other one will be like a statistics class. Although where Precal fits in there, because Precal's like still a class a lot of kids need for college, is going to be our question, because the state is saying you can take Precal right after Math 2. But I don't know if I feel that confident in taking Precal right after Math 2. I feel like you need 3 to get a little more practice with some stuff. But well, that won't affect any of you guys anyway, because you guys are already here. But anyway, regressions are really important. This is what a lot of mathematicians are doing. Like if you work where you are analyzing things, this is a lot of the stuff that you're doing. One example, whenever at the beginning of the year, the state gives us, we have this like program that we go into called EVOS, and it gives you every kid, and it gives us predicted scores for your like EOCs. So it has like formulas where they have said, oh, well, if we, you had this score and this score and this score and this score, and then so, oh, we predict that you will make this level on your EOC for the class. I think they do it for you guys. I don't look at it nearly as much because we don't have an EOC. It's kind of different there. But I definitely always look at that for like my EOC classes. And so what they're doing is they're coming up with a formula that is saying, well, we see these trends, so we're predicting this to happen, right? And then they use that for a lot of different things, but one of the things they use it for is like calculating growth. So they'll say like, oh, we think that Aiden is going to make a well, let's go higher than 25th percentile. It's pretty bad. 85th percentile. And so if Aiden gets 85th percentile or better, they're like, oh, good job, Aiden. A lot of times you don't even know what you actually got. But they take all that data for teachers, and then they put it in so that we like meet growth or exceed growth or don't meet growth. So like if the kids in your class are doing better than they were expected to do, then that's good for you as a teacher, and you'll get the green or the blue. The blue is the best. You do not want to be red. That is the worst. So you can kind of use it for like looking at what you're doing to see like how effective you are there. So this is so much of what mathematicians do, making models so we can make predictions for them, right? This is involved in things like scientific research, things like epidemiology, like the spread of contagious diseases. There's all kinds of areas where you can use this sort of stuff. So I think it's really important. I think that's why the state wants it to be more of a focus in like the future. So the idea of modeling, also called regression, is a major component of the AP Precal exam, and we will look at it throughout this course. Hello. No, he had an orthodontist appointment. He was supposed to tell you that yesterday, but he probably will not be in for your class. He'll probably take a period and move back. All right. That would be lovely. Or I can send him up there. Okay. All right. Thank you. Hunter's supposed to tell Miss McComb he was not going to be here this morning because he had an orthodontist appointment, but apparently he did not. Surprise, surprise. Okay. So, whenever you have regression models, if you are actually doing a regression model, you want more data than we are using in class. Because what we have here, for example, one, the age in weeks and weight in kilograms of 5 randomly selected babies from a particular pediatrician's office are listed in the table above. A linear regression, y equals a plus bx, can be used to model these data, where y is the predicted weight of a baby in kilograms. That is X weeks old, and they're going to ask us some questions here. So, in real life, you want to have a lot more data than this, because you can have a lot of variation, right? So you want to have, hundreds or thousands of babies that you were looking at before you're going to say, oh, well, a baby that is 6 weeks old should weigh around this much, right? Because there might be a really fat baby that is involved right here. And if you only picked 5, that fat baby is going to really affect that there. Or there might be a little teeny creamy baby that weighed 2 pounds whenever it was born. And it's definitely going to be like way off of this track. So you need more data. However, we are only using small data sets for what we're doing in class because, number one, it takes forever to type those in. Number two, the more numbers you type in, the more likely you are to make a mistake. So we're thinking about the process and how to do this, and understanding, like, in the real world, you would have a lot more data that you would consider. So we are going to first write the equation of the linear model for this data. So we're going to go to Desmos. Desmos has made this so easy these days. I like to split screen mine, so if you guys will all go to Desmos. And the first thing that we are going to do, we're going to hit the plus button over here in the corner and add a table. And then we are just going to put our data into the table here. And double check yourself to make sure everything that you type in is correct. Because if it's not, then you're going to get everything wrong after that. Even one number being off is going to cause you to miss everything else. Okay. Now, I have listed out here the regressions that you can use for linear, quadratic, cubic, and quartic. You might remember doing that from Math 1 or 2 some. However, they have made it even easier than it used to be, because now they have this add regression button up here in the corner. So if you just click right there, it has it all stored for you. You used to have to type in y1 squiggle ax1 plus b, and then it would give you the values for your a and your b and all of that stuff. This still works. You can do this if you're like used to doing this. It's also maybe helpful if you need a function that is not one of the preset ones here. However, pretty much anything they're going to ask you about on the exam is going to be one of those preset ones, so you really shouldn't need to do that. Well, I don't know. There might be one type of question you might get that's a little bit different. But So we can just use this drop-down menu now. In this particular case, they asked us for a linear regression. Now, it does say y equals a plus bx. Some statistical models use this instead of like y equals mx plus b, but it's just the same. The b here is your slope, the a is your y-intercept, so you can just choose that linear regression there. If they write it like this and ask you for a and b, make sure a is the number not beside of the x, and b is the number beside of the x. We then are going to interpret these results. So here you can see that we've got the a and the b value are given. If you do it this way, the a and the b value will be given, but they already plug it in for you here. So like this would be your values that you have here. Also, right here, notice that we have R correlation coefficient and an R squared here. So this R right here is called the correlation coefficient. It tells you how closely your line fits the data. If it is 1, that is like 100%, it is perfect, right? So it goes exactly through every point. So the closer to 1 that your correlation coefficient is, the better. Now, we won't get into like exactly how correlation coefficient is calculated, but correlation coefficient, sometimes when we're dealing with cubics and quartics and those sort of things, we can get a negative R or here. Well, actually, no, it can even happen with a linear. It's whenever your like line is decreasing, you'll get a negative R instead of a positive R. Still, closer to -1 is going to be a good fit. But it makes it hard to compare it with things like your like quadratic and those sort of things. So sometimes to compare to other models, we need to use the R squared, because by squaring that number, it's going to make everything positive, whether it was negative or positive to begin with. So sometimes we'll have to look at that R squared. I guess we should write down our answer for this one. Our equation for our linear model is going to be y equals, I'm going to write it in the form that they have told me to write it here, where they got the a plus bx, so the number without the x is first. So that is 3.545 plus 0.185x. If it's a free response, I don't think they're going to count off if you write it in the other direction there. But okay. Also, you don't really need to do it very much for this problem, but if you want to zoom to your data set, there is a little zoom fit button over here in the bottom. If you click right there, it'll kind of zoom in on those points so you can see them a little bit better. Sometimes you really need to do this because it's not even showing up in the frame. That one was not too bad. All right. Okay, so B says, using the linear model from part A, what is the predicted weight in kilograms of a baby that is 10 weeks old? So you have several options on how to go about this. Here, we want to use the linear model. So when it says use the linear model, it is talking about the equation, right? The model is the equation. You have to be especially careful for this if they ask you about a number that's already on the table, right? So if they said 8 weeks old, you don't give the number that is on the table. It's asking you to use the linear model, which is the equation that you came up with. So we want to take 10, and we're just plugging it in. You can do it by hand. You can do 3.545 plus 0.185 times 10. You can just plug in 10, all right? And then see what you get there. And we get 5.395. kilograms. Some other options. In this case, the number of weeks old, is that my X column or my Y column for the age? Is that X column or Y column? It's our X. So if I go over here and I type in X equals 10, it's going to put me a line right there. I can just see where those cross. Notice it's at 5.395, which is the same answer that we got there. I think what we would have to do if we want to use function, like we'd have to go down here, copy and paste that, do like f of x equals this, and then we could do f of 10. Same answer, right? So lots of ways to get that number right there. Okay, questions? Okay, for C, it says the weight of a sixth baby is 5.3. Using the model from part A, what is the age in weeks of this baby? So, using the model, again, means use the equation, right? This time I've got 5.3, but where is 5.3 going to get plugged into that equation? On the y, right? So, the quickest way to do this is to type in over here, y equals 5.3. And if you do that, it's going to graph you a line at 5.3, and we can see that we get 9.48649. So that's the quickest way to do it. If you want to do it by hand, you got 5.3 is going to equal 3.545 plus 0.185x. And you would just like subtract that 3.545. And we get 1.755 equals 0.185x, and then we'll divide. We get 9.486. This is weeks. And you can see that is the same thing that we're getting there. When we're doing these types of problems, one of the biggest things is really keeping in your mind, what does my X stand for? What does my Y stand for? If they've given you a table from at the beginning, you know, I guess technically I should not be using X's here. I should be using T's and WT's, but whatever. This is your X coordinate. This is your Y coordinate. So you can think, oh, I've got a weight. Weight is the Y. Plug in for the Y, right? That's important for you to see. Okay, so we need to talk about something that I can't remember if we do in Math 3 or not. Have you guys seen this word residual before? I honestly can't remember if I do it with 3. Maybe we think we've seen it. I think maybe it's in there. Anyway, that's bad that I can't remember it. So, residuals. This right here, you want to make sure you have memorized. Residual is actual minus predicted. Actual is the value on the table. Predicted is the value you get when you plug it into the line, right? So, actual minus predicted. If you just remember that, that will help you answer a lot of these residual problems. The difference between the actual value and the predicted value is your residual. It tells you how far off you are for that particular data point, right? Using the same example, what is the residual of the baby that is 5 weeks old? Interpret the meaning of this value in context of the problem. So whenever we're looking for the residual for the 5-week-old baby, we're going to find the actual value from the table. So we'll go back up here to the table. The 5-week-old baby weighs 4.4 kilograms. So that is my 4.4 kilograms. And then the predicted value, for finding the predicted value, we want to plug 4.4 into our equation of our line. So if we go back over there to Desmos, if I'm thinking about what I need to plug into this, I need a 5-week-old baby. Is that my X that I'm plugging the 5 in for, or is it my Y? It's the X. So I'm going to say X equals 5. It's going to put me a vertical line right here. Now, be careful with this. You're looking for where this line crosses the slanted line, the line of best fit that we're looking at here. And we're getting 4.47 kilograms. Okay, residual is just actual minus predicted. So 4.4 minus 4.47 is going to give us negative 0.07. So, when we're looking at this, the interpretation is the most difficult part of this. It, to me, is very helpful to remember this was your actual baby. This is the predicted. Okay, so my actual baby, since I'm getting a negative here, weighed less than the prediction from the model, right? So I could say something like the baby that was 5 weeks old weighed 0.07 kilograms less than the model predicted for 5 weeks. Now, that is certainly not the only way to say this, because you could talk about the prediction. You could say the model predicted that the baby would weigh 0.07 kilograms more than the baby actually did weigh, right? So it's really like, as long as what you're saying is correct, you can word it however you would like. To me, since you're doing actual minus predicted, I think it's kind of easiest to word it where you say the actual thing you're talking about is this much more or less than the predicted value, because it's already kind of in that order for you. But either way, it's fine. Okay, of course, this is, something that they definitely use. If you have that, they take all kinds. In general, anything with a constant rate of change is going to be linear. Quadratic models are going to be linear rates of change. So look at the difference in that word right there. A linear model has a constant rate of change. What's another? Oh gosh, I didn't mean to mark that out. Thought I had the highlighter. If we have a constant rate of change, what's another word we use sometimes for that rate of change? Slope, right? So we have a constant slope. So whenever we see what they've told us here, roughly linear, gosh, keep doing that. Linear, I picked the highlighter. It's like lagging. Linear rates of change. Okay? Linear rates of change does not mean that the graph looks linear, right? It means the slopes are increasing at a constant rate. Think about what we did with our tables. Whenever we had a quadratic, like a quadratic of 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. That's definitely a quadratic right there, right? So the rates of change goes up 1, up 3, up 5. The rates of change are linear. That's like that second difference that we did whenever we looked at this. So up 2, right there. So the rates of change increase at a constant rate. The slope is getting bigger at a constant rate. You can look for symmetry right here. That's sort of like the maximum or minimum that you're going to see. And then this is going to be important right here. Contexts involving area are typically going to cause you to have a quadratic model for that. For cubic models, they are often useful for contexts that involve volume. Now, I will give a warning here. Sometimes, if you only look at the correlation coefficient, if you only look at the r squared, sometimes cubic will be best if you only look at r squared. But sometimes cubic will do crazy things if you get too far out. So because cubic has more variables, it can kind of like adjust in there a little bit, like better. So sometimes it will have a better r squared value than the quadratic. But if you look out a little further, it does crazy things like starts turning back up whenever really we should just see it continue to decrease. So you don't want to make all of your decisions solely based on just the r squared value if you're actually looking at the data. So let's just talk about some theoretical situations without actually having any data. For A, balloons are filled with water in preparation for an epic water balloon battle. Each water balloon is roughly spherical. The radius of each water balloon is measured relative to the amount of water it holds. So we're looking at like radius of the water balloon versus the amount of water in the water balloon. What do you guys think on that? Linear, quadratic, cubic? Cubic, because this is volume, right? The amount of water that the balloon holds is volume. Is everything lagging today? Okay. Totino's pizzas are on sale at the local grocery store. The price of one pizza varies between $1.99 and $2.19, depending on the variety. So, like maybe the pepperoni is cheaper than the supreme or whatever you have, but not by much, right? They're all pretty close to the same price. The total number of Totino's pizzas are counted relative to the total price of purchase. Okay, what do you guys think for that one? That one's linear. It's not going to be perfectly linear because they don't all cost the same, right? But they're pretty close to the same. So that's going to be linear because each pizza that you buy is going to add about $2 to your total cost. A sprinkler is placed in a yard to water grass. The sprinkler rotates in a circular pattern and waters all the grass between the sprinkler head and the furthest distance it reaches. The radius of the circular path is measured relative to the area watered by the sprinkler. So we're looking at radius versus the area that's watered by the sprinkler. What do you guys think on that one? That one's quadratic. So if we remember specifically with area and volume, those are going to help us really know which one we're looking at. All right, let's look at a few more contexts that we're going to have here. So this particular one, actually, I said context, but this one example 4 has no context. So we are going to type this into Desmos. You need to decide which one fits best and use the characteristics of the table to help you. Actually, okay. Let's look at the data before we type it in Desmos. Which type of function do you think is going to fit best in this particular case? Okay, quadratic. I definitely think we should probably go quadratic. I'm interested to see what it's going to say for cubic, because we'll look at that as well. It could possibly be cubic, but quadratic definitely seems to fit this because our data increases and then decreases, right? Linear would definitely be off of the table here because linear should not change from increasing to decreasing. So I'm going to go with a guess of quadratic. So now I want everybody to type this in. I'm going to freeze my screen and type it in as well. Everybody type it in and see what you get for this one. Are they? Didn't look right. Okay. All right. So here's what I've got. That quadratic looks pretty good. In fact, I am getting an r squared of 1 for that. If I switch it over to cubic, notice I still get an r squared of 1. If Desmos tells you there's an r squared of 1, it does not necessarily mean that it is exactly 1. It is just close enough to 1. Desmos had to round it to 1 there, right? It might be 0.999999 there. So, between these, it would seem, that those two are the same as far as their r squared value goes. I'm interested to see what this cubic does if I zoom way out. If I zoom really, really far out, this cubic has like this weird, it turns back up on this side, right? Which is for negative values anyway, and depending on what we're talking about, you may not even consider negative values, so it might not matter to you. But I don't like the cubic because of that right there. But if I go with the quadratic, we know the quadratic is not going to turn back up because a quadratic has a parabola shape and it's not going to turn back up. So in this case where you're getting the same with both and this fits the data really well, I would definitely just go quadratic. Cubic's going to give you very similar numbers that aren't going to be like enough better for it to apply. So my equation for my regression here would be y equals negative 4.88317 x squared plus 15.95805 x plus 4.999564. Something like this, like, I would not give this to you and count it wrong if you put cubic for it, but the cubic is like just unnecessary in this case. All right, let's look at the next question. Okay, hello, sir. Oh, this is your last appointment?
Yeah.
Oh, so you don't have to go back? How are you? Hey. Yeah, we're still. All right. Okay, so this is the U.S. Per capita total cheese consumption for the years shown above, which I am pretty sure I did actually go look up. I'm not sure how accurate my sources are. I did not cite my sources for cheese consumption. But in 1995, the average person ate 29 pounds of cheese per year. And you can see that our cheese consumption has increased here over the last several years, to where in 2020 cheese consumption was at 39.4 pounds, which is something that I do not normally think about, but would kind of like to know how much cheese I eat in a year in pounds. Not enough to actually track it, but it'd be interesting to know.
It's kind of low.
Huh?
It's kind of low.
Thanks.
I think it'd be like in the high 30s and the low 40s.
I do love cheese. I feel like my cheese consumption might be higher than average too. Yeah. So that'll be interesting to think about. Obviously, this is kind of a silly thing to think about when you think about, like, personally how much cheese that you eat. But if you're in the cheese industry, right, if you make cheese and sell it for a living, this is actually something that matters for your business, right? So even something like this could really matter. So I'm going to have you guys go through this last part right here on your own. So put it in, answer those questions for me, and we'll see what we get. Oh, we need, actually, let me tell you one thing before we begin. There is something important that they have done on this, and they do pretty often for these types of problems. If you have already started typing it in and you're putting in 1995, 2000, 2005, and so on, you're going to get different answers than what it says the answers are. And that is because for part A, it says, let the year 1995 be represented by x equals 0. They do this pretty often, mostly because of the limitations of technology. If you're putting in those really big x values, particularly if you also have large y values, sometimes the calculator just gives up on that, particularly when we had to use the TI-84s. So this is something that we do pretty often. So instead of entering 1995, you're going to enter 0. So what would we put in for 2005? 2005 would be 10, 15, 20, 25. Okay, so we want to enter those as our x coordinates. So be careful, look out for this, particularly whenever you have large numbers for your x values. They may ask you to do this on a problem. You'll still get some of it right if you forget that, but you won't get everything right. So, now continue on your own.
It doesn't matter which version of the equation needs to be in
I guess it's wanting linear here, because it asked you to find linear in A. So I guess we want to go linear.
Let's talk about like 1995 versus 0.
Right, it will not matter. You can answer both of those questions and still get the right answer, even if you have 1995 in there. You just won't have your y, I believe it's your y-intercept on your equation will be way different in part A. Yeah. In general, the answer for the AP exam is keep at least 3 decimal places. So if it's anything that you are getting I like the data is rounded to 1 decimal place, but the rule on the AP exam is that everything that you do has to be correct to 3 decimal places. If you keep more decimal places, it's fine, but you can't keep any less than that. So that's generally what I try to do in class too. So we're well prepared for that. Get y equals 0.372571. Actually, let me do this. Oh, no, I didn't. Okay, this is fine. X plus 29.87619. In general, you only have to round to 3 decimal places, but I just write the whole thing down for that part. They don't count for having too many decimal places. And your answers will be more accurate if you keep everything there. So is this what everybody got? Make sure I didn't type anything in there. Okay. All right. So we're supposed to use the model to predict what the annual U.S. per capita total cheese consumption was for 2013. So I can't just plug 2013 in. I'll get a ridiculous answer, right? Because 1995 was 0. So I'll have to do 2013 minus 1995, which is 18. Is this my X or my Y? X, because it's the year. So X equals 18. I'm going to type in X equals 18. And I'm going to get 36.58248. Now, I will say this. I cannot give partial credit on a problem like this if you get it wrong. If you write down 37.58248 because you just wrote down the wrong number, you will get 0 credit. So what I would suggest for this, you're plugging in 18 for X. So I would suggest that you do this. Y equals 0.372571 times 18 plus 29.87619. And then put that equals 36.582 pounds per person. Or pounds per year. Pounds per person per year, I guess. Pounds per year would be fine. For that. If you write it like this, and you just make a mistake, maybe you've got something typed into the calculator incorrectly, you're still going to get the majority of the credit for this problem because you clearly knew what to do and made a slight error versus you just wrote down the answer and your answer was wrong for that. So I would suggest doing this even if you're not solving it by hand because I can give some more partial credit for that. And then we want to know in what year would we expect the total cheese consumption to exceed 45 pounds. So if we're talking about 45 pounds, that is a y coordinate, right? So we're going to type in y equals 45. here, and I'm getting 40.59305. Again, first of all, that doesn't need to be our final answer because it says in what year, and that's not the year, right? That's how many years since 1995. But in order to maximize the possible credit that you can get, I would do this. 45 equals 0.372571 x plus 29.87619. You don't have to show work for solving this, but you're showing me you knew I was plugging in that 45 for the y. Then you can just say that x equals, and I would write down that whole number that you're getting, 40.59305. This is not your final answer, but you're showing me the steps you are using to get there so that if you make a mistake or an incorrect assumption, that you still got some credit for that. Then this is years since 1995. So you're thinking 1995 plus the 40.593, and we're 40, not 10. And you're getting 2035.593. I would write this. Now, there can be some ambiguity here whether or not that is going to be 2035 or 2036. You're looking for when the model first exceeds here. But 2035 point anything is still during 2035, right? It's not 2036 yet. So I would say during 2035 is the best answer for that. If it's multiple choice, I do not think they will give you 2035 and 2036 as answer choice options. If it is free response, putting this stuff over here gives me more room to be lenient on whether or not you chose 2035 or 2036 for that. Okay, questions? Okay, so, I should also mention here, if we see this trend forever, is our cheese consumption ever going to go down? If we go with our model, will our cheese consumption ever go down? So, like, our great-great-great-grandkids are going to be eating upwards of 100 pounds of cheese a year, right? If we raise them right. Is that likely to continue with that pattern forever? In fact, there's a decent chance we might see the cheese drop. If big cheese lobbyists lose their hold on things and they start telling us all that we shouldn't eat cheese because it's killing us all. This might be true, I don't know. It's probably not. Then we might see the cheese drop back down. So it is important whenever you're looking at things, you can't make assumptions about trends for long periods of time. So this 45 pounds per year, it might not be a good assumption, right? Because we don't know that